Welcome to Study Loop.
So we're told a woman with a mass of 50 kilograms is standing on the rim of a large disc that is rotating at 0.8 revolutions per second. So what we got this disc like a merry-go-round or something rotating, and we have some woman standing on the edge of it here. And so this thing is rotating, around. Well, it doesn't really matter which direction. We basically, does it actually say no? Because they ask us for the angular momentum, and the angular momentum will be basically in the right hand rule direction of whatever we call positive here, or whatever direction we'll say it's rotating. Now the disc weighs 110 kilograms and has a radius of 4 meters. So they ask us for the magnitude of the total system. So that means the angular momentum, the magnitude of the angular momentum of the total system. So that means we have two pieces, and there's various ways we could do it. We could calculate a mass moment for the system as a whole, or we could just piece together the angular momentum in pieces. So we can either piece together the mass moment or piece together the angular momentum. Either way, we should get the same answer. I just calculated the angular momentum for each. So the angular momentum of the woman is her mass times the distance from the axis of rotation times her velocity. And so her mass is 50, the radius is 4. The velocity, again, we need to convert to radians per second, so we need to multiply that by 2 pi. So this is the angular velocity, and then her total velocity is the angular velocity times r, which is 4. And so we can see we get basically m1r squared omega. And that if we look at, m1r squared plus, and the other thing is 1/2 m2r squared, that would just be our total j. And we'll see that we all multiply both things by omega, so it winds up being, L total is just j total omega. And L1, because L1 equals j1 omega, and L2 equals j2 omega. And so again, the omegas came out, and so we could have just added the j values. Let's see here. I didn't actually calculate j for this because I just used it in terms of the linear velocity. Anyway, let's see here. I should write that in here, that this is also equal to m1r squared omega, where this is the mass moment about this rotation axis of the woman. Now, for the disk, we have, L2 is j omega. J for a uniform disk is 1/2 m/r squared. So we have the mass of the disk and we have its radius. So we get 1/2 times 110 times 4 squared times, again, omega we need to convert to radians per second. And plugging everything in, we get 4,400 kilogram meter squared per second. Up here we got 4,000. So, they're actually on this very, very close to one another. And that's not surprising, because the mass is, half of this mass is close to this total mass. So, and we have this factor of a half here. Adding them up, we get the total angular momentum is just 8,400 kilogram meter squared per second.